Okay, I'm going to record me solving a problem. And I'll just go ahead and share my screen here. So this kind of problem feels very difficult to me. I know that there are 20 trees, and I'm just going to simplify the situation by saying there's A trees and B trees and C trees. There's 12 of these, and there's 2 of these, and there's 6 of these. And it says distinct ways. And so what I'm thinking is that like the A's are kind of indistinguishable from each other. So if I have A, B, B, A, C, C, lost track of what I got here. I did 2 B's, that's good. And then I have 2, 4, 6, 8, 10, A, and then I have 3 ones. So this would be a way of doing it. And changing the place of the A's doesn't make any difference. Switching the B's around doesn't make any difference. It's like switching the A's and the B's or the B's and the C's. So I know that there's some fancy formula that can do this for me, but I want to kind of understand an approach to solving the problem that doesn't rely on a formula. I just want to try to do some problem solving because I think ultimately that's one of the things that we want to model and learn in math class is like, how do we attack hard problems? And one of my favorite strategies is simpler, similar, which is to make a simpler problem similar to the one that I have. So I'm going to take A out of it for now. I'm just going to say, let's say I have 8 trees, 6 of one kind and 2 of the other. And how many distinct ways I order these? All right, so now let's say, let's go back to my A's and B's here. A is 6 and B is 2. So let's start with an A tree. I'm going to kind of do a branching technique here, and then let's start the B tree. So from the A tree, I have 5 more places, A and 5 more places. And here I have B and 5 more places. And at this point now, this kind of breaks into a sub problem, which is if I have, oh no, I'm sorry, 7 more places. And this is B and then 7 more places or trees. But this one kind of is easier because there's 1 B left and there's 7 places. So there's 7 different ways that could happen. Right. So I'm saying this particular branch here would have 7 ways of doing it. And just to prove, I don't want that to be a negative, just to prove that's true, I can kind of work through it real quick. B, and then I got my B, A, then B, A, B, A, A, B, A, B, A. So this B is going to take 7 different places, which means that at the end of the day, there's 7 different ones where B is the first tree. So in this one, I now have a simpler, similar problem where I have 7 trees. And I have 5 of one kind and 2 of the other. So I've sort of got a sub problem that looks a lot like this little sample problem that I built. And I'm gonna branch it again, saying let's start with an A tree, or let's start with a B tree. This one I already know there's going to be 6 of these because I have one fewer place to put my, right, I'm starting with a B. Dang it, stop doing that. So this will work on down like 7 through 6, 5, 4, 3, 2, 1. What's happening over here? Starting with an A tree, starting with another A tree. If I could find out how many of these I have, then I could find out how many of these I have. And at some point, doesn't this problem just mean, well, let's back up to this larger problem. Aren't I just saying, how many different ways can I choose 2 out of 8? Let's say the places are number. I'm abandoning this path because it doesn't feel productive to me. Let's say that but I'm gonna stick with my similar problem. Let's say that I have 8 places, and I'm gonna number them 1, 2, 3, 4, 5, 6, 7, 8. How many different ways could I choose 2? And the order doesn't matter because if I choose 2, 8, that is the same as 8, 2. Right? Because I'm just looking for these 2 B's to go into this lineup somewhere. And I want to know how many different ways that can happen. So that just feels like 8 choose 2, which I know is, and if the order doesn't matter, then it's the combination formula. So that's 28 different ways. So how does that help me with the larger problem here? What if I had one, let me try to get back to 3 trees now. I understand how to solve the problem if I have 2 trees. I got to think about places. So let's make a similar that's a little more similar by having 3 different types, but I'm going to have it be simpler by having only one of those. So let's see here. 10, let's keep the numbers relatively small. 5 A's. Probably simpler, similar 2. 5 A's, 3 B's, and 1 C. So the 1 C can be placed, now there's 9 trees. So the 1 C can be placed in 9 different spots. That's 9 options. We know that if we can counter options, then we can kind of multiply them out. And then how many different ways can B be put in? Well, I suppose the question that I'm wondering here is, if I've already pinned down C, there's 8 spots left. And so in the 8 spots, then I'm back to this sort of, how many ways can I put 3? And I think, just finish my sentence here, I think combin 8, 5 is the same. Oops. Is the same as combin 8, 3. Yeah, they're identical. Because I'm be asking the same question, but from the other side. So if there's 8 spots, there's 56 ways I can arrange my B's or my A's in those. And that means that there should be 9 times 56 total ways of arranging this, which is 504. Okay. That feels good. So then if I'm starting with, say, the small one, 2, how many ways can I put 2 spots in two trees in 20 spots? There's 190 ways. Now there's 18 spots left. How many ways can I put 6 trees in 18 spots? That's that number. And so the final big number would be 190 times, I'll just use cell references. This guy times this guy times this guy. 78. Okay, there we go. So this is my final answer. Okay, now the formula, the magical formula, the one that you're supposed to use is you start with the factorial of the large number, which is that there's 20 trees. And then you divide by the factorial of any of the smaller groupings. So there's 12 of those. I'm going to put times here. Factorial 2 of these and factorial 6 of these. So this should end up being the exact same number as I just calculated. Yeah, it is. So that's a different way to solve. That's a sort of the formula way to solve the problem. But I wanted just to kind of model the problem solving approach that got me to that point. Now I'm not saying that that would work for you because these are difficult problems. You gotta kind of think through the situation, but it helped me kind of make sense of the situation. It's really a combination of the multiplication principle where you're looking at your options for one thing and your options for another thing, and then you can multiply them together to get all of your options. And the combination concept, which is if I have this many spots, how many different places can I put this thing? That's, if the order doesn't matter, that's the combine formula. Okay, there was one other problem I wanted to share with you. Let me go get it. I'll just pause this. Okay, so here's a problem from from Newton. And we're doing cards, so you guys should be familiar with that. The odds part is what makes this different from a probability question. The basic concept of odds, to calculate the odds, you do the probability of some event divided by the probability of the event not happening. And it makes a ratio. So let's take a look. Odds of drawing an ace or a 9. Okay, ace or a 9 should be 8 out of 52 cards. And I'm going to write it out like that. Of course, we could make it a percentage, 8 out of 52. This is what we've been doing. And then the probability of it not happening is 44 out of 52. And that would be this probability, which we call the complement. And so the odds is just basically the ratio of this to this. Now, I know my fractions pretty well, so I know what's going to happen here is I get 8 out of 52, and I'm comparing that to 44 out of 52. And long story short, we'd have to do like division multiplication and kind of simplify this, but basically the out of 52 is common to both of them, so it can really be simplified to 8 out of 44. Now, 8 out of 44, we want to leave it in this form and we want to fully reduce it. So it needs to be divided down. This is going to be divided by 4. This is going to be divided by 4. I think the answer is going to be 2 2/11. Or 2 2/11. So let me now switch over to the other screen. Here we go. 2:11. Right. Now you just have to pay attention as you go because you know, they may switch between odds and probability. You just have to read very carefully and you know, just be careful on what you're doing. So again, we think about this problem, we want the probability of it happening to the probability of it not happening. Then we want to kind of simplify it. So 2 red, 2 green, 1 yellow, 1 blue. What's the odds of not landing on red? So not landing on red should be 4 out of 6. And then I'm putting that in comparison with the odds of it happening, not landing on red. That's landing on red, 2 out of 6. And then this part I don't need to pay attention to because I'm simplifying the ratio. That's a 4-to-2 ratio. That's a 2-to-1 ratio. And so we should be able to get this one right. Let me take my annotation tool off, select that, submit that. Bam. All right. Those are the 2 ones that I think would be pretty complicated and hard if you didn't get some support. And of course, all of this material is in Newton. You just have to kind of dig for it and get the support, which is nice that the tools are there when you're working on it. So hope that helps. I wanted to make sure you had that.